Can you hear me? Yeah, mic working. Okay, great. Thank you, Srimanta. It's because of him I'm here. And I really appreciate, I've been having a great time at this workshop, seeing so many young people. IISc is beautiful, by the way, so almost tempted to stay there a bit longer. And this morning we heard a beautiful talk on complex oxides. So we're going to continue that. There's no growth here because I get all my films from him. He's one of the world's top growers. And Daryl Schlom and Ramesh and so on. So we have a good ecosystem of people who do really good materials so that when you spend time characterizing them, it's worth your time. So today, this talk is going to be about light-matter interactions. I'm going to talk about complex oxides, kind of things that Bharat Jalan talked about. And I'll introduce briefly what nonlinear optics is. In X-rays, we all know quite a bit already. Show you how we could, what are the opportunities in terms of discovering new phenomena. So I have a long list as well, just as you. So Argonne National Labs. So Longking Chen is one of the theorists you'll hear more about. Arun Lindenberg and Anudeep Mangu at SLAC and Stanford. The films grown here today are from Daryl Schlom's Paradigm Center, as well as by PLD, so no hybrid MBE today, from Ramesh and Lane Martin's group at Rice. All right. So this is just one slide on my group. It's called Unlock without a K. Ultrafast nonlinear optical characterization group. So we have an optics lab, we have lasers, and we shoot lasers at materials. So we just call it shining light on materials. Today will be all ferroelectrics, but we study a whole variety of materials. Here is, for example, a strongly correlated electron system, calcium ruthenate. You're welcome to go take a look. So this is one of the things from a characterization point of view that excites me. And all of this really has happened in the last 10 years. Ultrafast optics has suddenly come a long way. Now recently we got a Nobel Prize for attosecond lasers. So femtosecond has become very standard. Everybody has one, probably a bunch in IISc. Coherent X-ray is the other thing where everybody is building a synchrotron. I think India has to also start building some synchrotron. There is one, right, somewhere. And free electron lasers. And all over the world, and the beautiful thing about them is anybody can go use them. You can go use them, whether it's in Japan or United States or Europe or wherever, Korea, China, and so on. And so they have come along quite brilliantly. And TEM, when I was a grad student, we didn't have the resolutions you have today. Everybody says we have a Titan today. And so, we have pushed the limits of that. You can get 5 picometer kind of resolution. So to put that in context, a hydrogen atom, the smallest atom, is about 50 picometers. So about 10% of the size of the smallest atom is something you can see. So you can push length scales and you can push time scales through very short pulses. So there's a very unique opportunity today in terms of, in terms of theory, because we are at ICTS, all of this gets you much closer to DFT that we were talking about yesterday, right? So comparison with experiments one-on-one with theory has become, this is sort of the golden age for that. All right, so I have 2 small stories. One is imaging. So today it's all about ferroelectrics and polar materials. Imaging emergent polar phases in classic ferroelectrics. And I'm going to talk about a supercrystal, light-induced or light-created supercrystal. All right, let's get on with the story number one. I wanted to present a little bit introduction because I was told with grad students, it's nice to give some introduction. Light is very nice because, physicists would say, it gives you this whole energy scale to hit things with. So from all the way from electron volts to milli-electron volts, and if you go further up here, X-rays, kilo electron volts, right? And so various processes like electronic processes happen around EV, all of the phonons start kicking in around the milli EVs, tens of milli EVs, spin dynamics, free carrier dynamics. So if you want, so your material has electrons, it has nuclei, it has spins, the electrons have spins, they are magnets. And they dance at different frequencies. So you can really think of this as music. And by shining light on materials and seeing who is on the dance floor and who is sitting out, you can tell a lot about the bonding in materials, right? And so X-rays, by the time you get to X-rays, pretty much everybody is sitting out. Even the electrons are too heavy to dance. So that's why X-rays can sort of get through materials unless you're on resonance. Okay, very brief introduction to light-matter interaction. This is a classical atom, okay, very cartoonish, but it works, I hope. So you have a nucleus, and when you shine light, mainly the electric field we are talking about, there's also a magnetic field component, but exerts a force about 10 to 100 times smaller. So this is going to slosh around the electrons at these frequencies. We are talking about 10 to the 14, 15 hertz times per second. The electron is the lightest thing in the material, right? So it's going to slosh around. And when it sloshes around, you create what is called dipole moment, some negative to positive. That's the convention. So this dipole moment is also sloshing around. It's pointing up, pointing down, pointing up, pointing down. So when you have something like this has a name. It's called an antenna, right? An antenna, an atom turns into an antenna. When you shine light on anything right now, all of this magic, you're seeing me, I'm seeing you, you're seeing the screen. This is basically what's going on over there, right? And so if you take the electric field of light and you figure out how many dipoles are there, you add them up over a given volume per unit volume, you get what's called polarization. Polarization is a very common word, especially in politics today. But polarization is a great stuff, okay, in terms of solid state physics and material science. This is the polarization in the material created by the electric field. It drives a lot of the phenomena we perceive as the reality. This process is called linear optics, right? So the electric field and the polarization are linearly proportional. It's a very simple Lorentz model, and this is linear optics, right? And most of our day-to-day things are dominated by this linear optical behavior. So as I mentioned, this is an antenna. An antenna radiates out electromagnetic waves. So what it's going to do is this same atom is going to radiate out the same light that created it. So this is the electromagnetic wave on the left-hand side. This is the antenna on the right-hand side, oscillating dipole on the right-hand side. So the electromagnetic wave created the oscillating dipole created back the electromagnetic wave. This back and forth is called scattering, right? So that's the process of scattering. And that's why sky is blue. Otherwise, it wouldn't be blue. And blue gets scattered more than other colors and so on and so forth. So, some details. Okay, so where does nonlinear optics? You might have already got some idea there from that linearity. So imagine suddenly there was another atom that just pops up here, okay? So suddenly this electron cloud is going to run into that electron cloud. It doesn't want to. So it can slosh around more on that side than on this side, right? So now if it was a nice harmonic potential, you're just jiggling the electron equal amount left and right. Now it's going to do a little lopsided dance, a little more on that side, a little less on this side. That's an anharmonic potential well. So if in physics, material science, harmonic potential wells are very common. Anything that has maximum, minimum at the extreme you can approximate as harmonic wells. But when you start doing larger excursions, you start getting anharmonic effects. So one of the anharmonic effects is not only is this antenna going to radiate the same wavelength, it's going to radiate twice the frequency. It could radiate other frequencies as well. In general, you're going to have polarization, right? Proportional to electric field. This is linear optics. Now it can have square, cube, 3, 4, so on and so forth. You can do a Taylor expansion over larger. So as the electric field gets larger and larger, when you, essentially you shine lasers, which are more powerful, you're going to tap into each of these. Now, it doesn't have to be the same field square. It could be E1 times E2. There can be 2 fields there. There can be 3 fields here. And the whole thing is a tensor stuff, various directions inside crystals. It gets pretty complex, but that's the fun part of it, right? Or you can think of them, each of these terms, as a Windows menu. You click on it, the whole bunch of phenomena that just pop out. You can use them for various applications. So for example, the second order term is called doubling the frequency is called second harmonic generation. So this is one way to create colors in a laser lab. If you have only 1 or 2 lasers, but you get all the colors by putting different crystals in front of the laser you have. Okay, so I'm going to talk about ferroelectrics, which turns out, here, for example, barium in the corners, oxygen forms an octahedron. There's a titanium in the middle, and this titanium at lower temperatures pops up a little bit. See, it's not in the exact center of this. So the center of positive charge is slightly to the top compared to the negative charge of the oxygen atoms. So this is a frozen polarization, right? Frozen dipole moment for a unit cell. And that can be sloshed back and forth. The titanium can move back and forth by applying electric field. That's called a ferroelectric. So we are going to look at that. And this is sort of relevant to this because you see, if you think of this guy as the titanium, and this one is maybe that oxygen on the top, then the electrons of this are going to be closer to that than that, right? So it's going to do this lopsided dance again. And what that means is it's going to change the color of my laser light. If I shine a laser light over there, it's going to produce a new color which I can detect and say something about the dance or the electron distribution of that titanium, for example. So broken inversion symmetry, this is a good way to detect. Okay, I'm going to, for the next few slides, talk about this material, classic material, barium titanate, and also potassium niobate. Bharat grows very beautiful films of barium titanate. So we have studied a lot of films of this. Today I'm going to talk about, so it has this classic ROTC. One of your students was an ROTC student, right? I saw that in the corner. That's some American lingo. You can Google ROTC if you like. Rhombohedral, orthorhombic, tetragonal, cubic, this is the classic equilibrium phase diagram, right? And barium titanate room temperature is tetragonal, whereas potassium niobate is orthorhombic. Now it turns out that between here and here, there is a metastable state, which is monoclinic. So here, cubic, there is no polarization. That titanium is right smack in the middle. So there's no net polarization. Center of positive and negative charge are the same. But if it pops up or down a little bit, it develops a polarization in the vertical direction. If it pops along the phase diagonal, then it develops along the phase diagonal. And if it pops along the body diagonal, then it develops the rhombohedral phase, right? So these are the various phases. Now it turns out it may neither pop along this direction or the phase diagonal, but somewhere in between, there'll be monoclinic 1, or neither along phase diagonal nor body, but somewhere in between that would be monoclinic 2. These are not stable phases, by the way. You won't see them in the phase diagram. In single crystals, you shouldn't see them at all. But you'd be wrong to not expect them because I'll show you that they're there in single crystals too. You'll see them. So regular optical microscope, you put one of these crystals, single crystals, you'll see beautiful domains like these. These are electrical domains, the polarization, the direction in which the titanium is popping, for example. So this is like step ladder type domains. There is another step ladder going that way. When they sort of start trying to meet, there's a lot of stress around here. So these guys, instead of running into this, they form little needles, and there's a lot of stress here. Okay. So local stresses and fields could stabilize something else. And I'm going to show you those monoclinic phases will start showing up in this sort of region. Okay. So regular optical microscope, everything looks okay. These are tetragonal domains, classic phase diagram. But as soon as you start, so we developed this second harmonic microscope. What is that? It's just a fancy way of saying we come in with a laser of one color, in this case 800 nanometers, focus it, and detect twice the frequency, which is 400 nanometer in wavelength, double the frequency, half the wavelength, right? So it come in with, say, red or infrared light, go out with blue. So we are detecting blue. Okay, and we can scan and we can make an image. This is the same domains, beautiful tetragonal domains. And we can even detect that they are tetragonal. I'll say that in a few slides. So this is what we expect to see, and we saw it in some regions, but we look around a little bit more and you see this. The first time we saw this, we were like, what is this? All this shiny stuff. I mean, all of this is normal, but this is not. In fact, this is so bright that makes it look makes this look very dull. You know, this is actually quite bright, but it's just the color scale. So it looks like sunshine on a staircase, right? This is sort of very nice. So we were trying to figure out what this is, and I'll just give out the secret. This is that monoclinic phase. Okay, so we can go in, you can even see there's some fine structure in there, some beautiful sort of shadows and so on. They are monoclinic domains, okay? And so all we have done is instead of looking at the same color that comes in, and we are looking at twice the frequency, and things are popping out where otherwise regular optical microscope would not see these things, okay? And you can go and look at the symmetry of these things. We figured out they're monoclinic because we could go to a point A or point B and do what is called polarimetry. So you could rotate the polarization of the incoming light, that's that circle, that's the same as this, and you can detect the output blue light at various polarizations. So red versus black is two orthogonal polarizations. And you see all these beautiful, you know, peanut and cloverleaf and so on, nice shapes. They have some information about the crystal structure, and you can fit them. Solid lines are theory, and from that I can tell you this is 4mm. If you know point groups, this is 4mm point group. Okay, beautiful, as expected, boring in some sense. But if you go to that sunshine region and you see, oh, suddenly it looks pretty much like that, except if you pay attention, these lobes are longer than those two lobes. This one has got some slight asymmetry, some kink to it now. You start trying to fit all of this with tetragonal domains, you cannot capture these little details. But if you lower the symmetry to M is monoclinic, then you can fit this very nicely. And we had to assume that this plane is the mirror plane, monoclinic mirror plane. So we have a hint already from this sort of polarimetry that there is a monoclinic phase hiding in plain sight among the tetragonal domains, even in a bulk crystal, okay? But you should not always rely on optics because we don't have the resolution. Plus, we are doing all this modeling too, you know, sometimes you can fit an elephant if you have enough equations. So you have to be very careful. X-ray is always a good thing, you know, so this is an X-ray beam line, which is called hard X-ray nanoprobe at Argonne National Labs. They can take X-ray and using Fresnel zone plates, so they can focus it down to 30 nanometers. X-rays are very hard to focus because they don't interact with the material. But they can do that with this Fresnel zone plates. Of course, you can Bragg diffract, so you can use that idea and use single crystals and some patterning to focus those beams, and you can scan them and make images. Okay, so it looks a little funky, but don't worry about it. Just look at the intensities. It's pretty much like your read streaks, but in this case, these are Bragg diffracted beams, and so this first line is tetragonal, and you see a little split in that sunshine region. That little split is that monoclinic M phase, okay? And you can do a bunch of things. You can read this paper, and you figure out what this monoclinic phase means. It is simply, if you take the black cube, right, you have nice 90 degrees, you kind of skew it a little bit by 0.018 degrees. Very tiny. That's it. So as soon as you skew this, it's no longer tetragonal, and the polarization, that electrical polarization, does not have to be along the edge. It can sort of be anywhere in this plane. M, the mirror plane, only restricts the polarization to be in the plane anywhere. So that's one of the reasons you saw those shadows. You know, all of those were wavy because they are monoclinic domains and they can weave around this monoclinic, this mirror plane. So one of the powerful things is, you know, we think of new material engineering, or I want to, you saw that intensity, you know, in here, it's so much brighter, 10 times brighter than here. How do I get an optical response 10 times stronger? You think maybe I'll alloy this with something, put very high pressure, or do some crazy stuff, right? No, all you have to do is just break that symmetry a little bit by 0.01 degrees. You get 10 times enhancement, right? So symmetry breaking is a powerful way of materials engineering as well. Sometimes, you know, a very small amount, in this case, it's a shear strain. Okay. So this is the optical image of the SHG microscope of that same sunshine region. This is the X-ray of this exact region. Using that little split peak I showed, you can make an image, and it's sort of matching that region. But now we also know from here what's happening at the unit cell scale. Okay. All right. So that was barium titanate. I have one more story to tell, so I'll move forward. Potassium niobate, remember it's sort of the second cousin. It's also got the ROTC, but except it's at room temperature orthorhombic. Now we thought, maybe that one has sunshine too. Let's buy some crystals of that and take a look at this. And it does, okay? So ignore these are markers that we deposited, but you can see domains, a whole bunch of domains. These have 120, 60, 90, 180 domain walls. So it's more complicated because symmetry is lower, but you see all this sunshine, they are monoclinic domains. And you can go in, you can sort of do all of the due diligence, but I'll change gear and I'll say, what if we do what Bharat does? You know, grow these films. Okay, potassium is a tough one. He won't put it in his MBE. But Daryl Schlom has this center where he has his own MBE where he won't let me put it, but he has some other MBEs where he'll let you put anything. So we did go there. My student Sankalpa Hazra, who is from IISc. Thank you, Middey. He worked with you, Srimanta's lab. And he went and grew these films on various substrates. These are various candidate substrates and plus strontium titanate. Potassium niobate is over here. He grew it on 3 of these substrates. And what does that do? You epitaxially grow on something with a different lattice parameter. So in this case, a smaller lattice parameter compared to potassium niobate, right? So you're going to, so this is going to have to fit to the template. So it's going to have to shrink. So when it shrinks, it's under compression, right? So all of these films, these 3 films are going to be under compression, biaxial compression. And I'll show you what happens. This is the phase diagram for temperature versus strain. This is all compressive strain done by Longking Chen, who is an expert in phase field modeling. He is my colleague and probably the foremost expert on phase field modeling in the world. This is, he has a very bright student, Aidan Ross, who calculated this. So zero strain, it's got a bunch of transitions. It's not zero stress, but zero strain. But you just need about 1.5% compressive strain. And all of this green region is just one phase, tetragonal phase. Okay, you squeeze it like this, it pops out. It's tetragonal, it's long this way and compressed this way. But the other thing is, you know, when you heat this, at some point, it loses the ferroelectricity and becomes paraelectric. It's no longer electrically, the center of positive and negative charge are not separated. That phase transition, you see, has moved from here up, and then we had a break here because it's such a long diagram, and then it's going over here. These are 1,000, 2,000, 3,000 degrees, Kelvin. Okay, so the typical transition in potassium niobate is about 420 C, which is about 700 Kelvin. Now just a little squeeze, and that transition has gone to 2,000-3,000 Kelvin, well beyond its melting point. So it's sort of moot whether that's even useful. But you can push out all of the transitions below, all of this stuff, all of that transition above, no transition, just a single phase from liquid helium all the way to until melting point. Okay, so just a small little strain on that film. And if you think of how much that shifts as a function of strain, these are various materials that have been shown, some you have worked on. Potassium niobate is over there. It's extremely sensitive to strain. Okay. And it turns out that's because it has strong electrostriction. We did the second harmonic stuff I just talked about. It's a good way, as I told you, to measure different phases. This is bulk crystal. It has the R, O, T, C. See the 4 transitions. In this case, the 3 films. This one, lowest strain, it's tetragonal mostly and becomes monoclinic at low temperatures, pushes it further by strontium titanate, which is about 1.5–2%. Excuse me. Strain, you don't have any other phases. Okay, so just as the thermodynamic phase diagram predicts, no other phases, all pushed out at single polar phase. You can measure the optical response, that second harmonic response is huge compared to the bulk value and compared to the other compounds. All right, I'm going to skip this in the interest of time, and I'm going to say that strain and symmetry breaking are very powerful tools to create metastable ferroelectric states with superior properties. So often we think of strain like how much can I pull, how hard can I pull, how much can I squeeze? But I would also like you to think about just what symmetry can I break with the least amount of effort. It's kind of like, you know, some of this Tai Chi, Kung Fu kind of thing. You do like small amount and the person goes tumbling over. So you have to, you have to think of that. Symmetry is one of those tools. Okay. Let me move to the story number 2. I want to have enough time where this is the phase field model of what is called a supercrystal. Okay, this is what we call it a supercrystal. What is super about the crystal? Well, I came up with it so we can sell it. But more importantly, its unit cell is huge. That's why. So think about this direction is about 30 nanometers. The other dimension, one of the other dimensions has 2 periodicities, 11 and 30. And the third dimension this way is 25 nanometers. So typically if you take a standard crystal, say sodium chloride, your table salt, and look at the crystal, and right there is sodium chloride. Okay, nice, beautiful crystal. If you zoom in, you got each sodium has 6 chlorines, each chlorine has 6 sodium. They are happy. And the typical distances here are angstroms, a few angstroms, right? So now we are talking about nanometers, which are tens of angstroms. So in other words, a sodium here might have to talk to sodium over there. It cares, huge unit cell, and this unit cell is repeating to make a bigger crystal like this, right? Okay, so why would somebody here start wanting to talk over there. The only reason for that is they are not happy with their neighbors. Okay? So one of the tricks for long-range interactions, or if you want to make extended structures, is to have local frustration. So that's sort of the trick here. If you make somebody unhappy with their neighbors, they will seek out the neighbors in the next block or the next street over or something else, next city or so on and so forth. So you have to frustrate the system, frustrate the neighborhood of the system in some clever way to maybe realize some crazy things that are not otherwise feasible. So that's what we did. So this is work by Ramesh and Lane Martin and Sujit Das, who grew a bunch of these for this study, is here at IISc. He's now a faculty at IISc. Okay, so Sujit is not here, but thank you, Sujit. I'm hoping to meet with him. So lead titanate and strontium titanate. Lead titanate is just like the barium titanate I talked about. It's a ferroelectric, and this is not a ferroelectric. So what their group has done is grow multi-layers of 16 unit cells of one, 16 unit cells of another, and keeps going. Yeah, how about we do it at the end, because we have 9 minutes, and I think is that okay? All right. We'll keep that in mind. I'll try to answer that. Okay, so 16 unit cells of one and the other. So remember what we're trying to do. We're trying to frustrate the neighborhood. So there are two types of frustrations here, which is very clever. One is, this is under compression. When things compress, you pop out, right? So the ferroelectric polarization here wants to be up and down because of this compression. But this is compression, this is tension. So compression, tension, compression, tension. The other thing is it's ferroelectric, not ferroelectric, ferroelectric, not ferroelectric. So this is polar, this is not polar. Now at the interface, you have del dot P, divergence of polarization, is going to have a lot of bound charges here. Because suddenly you have polarization, then nothing. So obviously it's going to pile up a whole bunch of positive charges and negative charges, but they have nowhere to go. So the system is frustrated. Okay. So what does the system do as you grow it and cool down? This is a TEM picture, these yellow arrows are showing. It starts going up, but as it approaches the interface, like, oh no, I don't want to go up, it turns right or turns left. Right? And so it just starts turning and then starts going down and like, oh no, I don't want to go down. It turns left or turns right. So it ends up giving these little spring rolls, they sort of, we call them vortices, polar vortices. Okay, so polar vortices, they're long tubes. And these form automatically because of these two types of frustration. All right, what did we do? So that was work from Ramesh's group. Many years ago, they were predicted by Longking Chen and my group to have these vortices, but we never experimentally realized them. Ramesh's group did that. So what we did was we took their system and thought about when a system is frustrated, can we push on it? Right? So you sort of push on it with electric fields or charges or temperature, whatever else, and maybe it goes and finds another state. And that's exactly what happens. So in this particular case, as I mentioned, these interfaces have built up charges and they are not happy with having all that charge there, so they're doing all this other stuff, right? So what if I flood those interfaces with charges, okay? Then maybe the system is happy being straight up. It won't try to go left, right, and all these other sorts of things, right? Okay, so the one way to do that is to optically pump it. So we go above the band gap of lead titanate at 400 nanometers, 50 femtosecond, we pack some power, you need certain threshold to induce enough charges on the order of about 10 to the 20, 10 to the 21 carriers per centimeter cube. And you flood these interfaces for a brief period of time, 50, 100 femtoseconds. So you're sort of taking a pack of charge and and seeing what does this do, right? And to our surprise, we didn't know what would happen, but Vladimir Stoica, who is a research professor in my group, had this intuition, he tried it. And so this is what happens, okay? This is an X-ray image. So you're literally taking an X-ray beam and making an image, just like we talked about before. So you're seeing a strain map of two different mishmash phases. This is the vortex, which is the blue part. All this blue is all these little vortices if you zoomed in. This is zoomed out a bit. And all this red phase is the standard, what we call regular A1, A2 ferroelectrics. They're in plane ferroelectric domain. So one are these vortices, the other look like that. It's a mishmash, okay? You hit it with one single pulse with this packed with charge, right? It's very important to be above the gap. And boom, all the strain contrast is now practically zero, right? Somewhere around here. Now with X-ray, this is real space image, but with X-ray, something remarkable happens. So this is the reciprocal space image, right? RSM. And you are looking at what happened. So this is a three-dimensional reconstruction, this is just the data of all the Bragg peaks that are before and after, okay? So before, you see there are some peaks in this vertical direction that just comes from the layering that you have done by the growth, right? So that credit just goes to the growth people. So Ramesh and Lane's group, and actually Sujit might have grown this one. And once you hit it, you see all of these side peaks, all of these in-plane periodicities are showing up. It's almost like some Indian goddess with many hands, you know, it's just very sort of gorgeous looking Bragg diffraction, but it's a lot of work also. Now you have to take this and reconstruct the real space image and figure out what this is. This is a supercrystal. It took us a couple of years to figure out what that is. So I'll walk through one cut of this. So L is this way, K is that way. So this is KL in the reciprocal space. So before, you can see there are two phases sort of repeating. This periodicity is that 16 unit cell kind of periodicity. And later on, it just becomes this after a single pulse. I'll show you a few cuts. So this spacing is 12.5 nanometers. That's the lead titanate, strontium titanate, lead titanate, strontium titanate. But after you hit it, you see there is this half order peaks here, which means half in reciprocal space means double in real space. So 12, this is 25. Right? So there's something about this where this is lead titanate, strontium titanate. The second lead titanate is not the same as the first one. And then you have to go to this one to get the same thing as that. So it's doubled the unit cell in the vertical direction, right? Something light has done to double it, okay. And the same sort of thing happens in plane. In plane, there was no periodicity here. Suddenly there is a 30 nanometer periodicity in the plane along these spring roads that we are talking about. So, okay, what happened here? So phase field modeling was important. So phase field modeling takes free energies. It's a continuum model, free energy for the Landau free energy, which is polarization energy, elastic energy. Electrorestriction couples these two energies, and gradients take care of interfaces, gradients and polarization. Okay. So to put in all of this stuff, I'm sort of running out of time. Electrons, holes. This is Klein-Gordon type equation for the polarization dynamics. This is a paper I wrote with two brilliant people in Kolkata many years ago. It turns out we kind of, these guys, along Chen's group, discovered it, and they've written a beautiful code, and all of these simulations I'm going to show you. This is critical. This is elastodynamics, and this is the fields, right? This is Poisson's equation, and these are various carriers. Okay, so in terms of energy, what happens is you start with some mishmash here, and the total energy, you get the supercrystal here. It has lower energy than that. So light somehow could find a little barrier, get over this barrier, and find this local minimum, okay? And if you break this apart, you see that the Landau and elastic energy goes down. So it must be good because it must have gone down enough, although electrical energy and the interface energy, gradient energy goes up. Okay, so if you look more carefully, there are all these swirls left and right. So you can see these swirls we were already seeing left and right, left and right. But now there are swirls up and down. So it's almost like, DNA origami. You've got some swirls like this, you got some swirls like this that were not there before, but light has created these things. We know that these simulations are okay because you can take the diffraction pattern you have measured, you can do Fourier transform and take the diffraction pattern from the phase field, and there's some matching. Not always perfect, but they're close for all of the various cuts that I just showed you one cut. Now I have to tell you something, that crystal we created stays there. So you create it, one pulse of light, the supercrystal shows up and it's there, it's yours. Okay, it's good until you heat it until 450 Kelvin's gone. Okay, now if you cool it back, it doesn't come back. So give me a few minutes and I'm almost done, a few slides. So cool it and it's almost, so it's gone. So it is metastable in that you need the light to create it, but you can erase it and it's quite stable, okay? So the question was, why did the light create? How did it create it? That's a longer story. This paper is almost there. It's going to be in print soon, but you can see it on archive too. We went to X-ray, very short X-ray pulses at Stanford Free Electron Laser System. So it's a LCLS, line coherent light source. And so this is an optical pulse coming, one pulse, it changes, right? Then an X-ray pulse comes before, at, later, at various time delays, that's the x-axis. And you can track what happens to various Bragg peaks. So here there was all this mishmash. Within a picosecond it collapses, then nothing. This is some very special soup. We call it the primordial soup. Okay? This primordial soup is hot, but because you hit it with a lot of power, but hot is not enough. You hit it with any random laser, it won't work. It has to be charged. Remember that all that wider band gap, like higher than the band gap, you're injecting carriers. That's very, very important. And so then it's hot and charged, and then it forms a metastable soup that normally would not exist at these temperatures. It cools down, and then a crystal comes out of it. This is the supercrystal. Okay? It's kind of like you dissolve, sugar or salt in water and boil it and keep it in a corner. And after it cools down, you get some crystals. This is sort of like that with the laser, okay? Yeah, so the phase field shows you mishmash, then forms a soup, then it slowly starts forming these vortices as well as what we call labyrinthine phase, and all of this with some strain dynamics turns into a vortex supercrystal. Okay, we know where the charges went because when you pump the charges, this is transient absorption spectroscopy, where we know that the electrons jumped from lead titanate to strontium titanate and holes from strontium to lead titanate. And right at the interface, they form these, the charges are separated, they form these dipoles. And they are very, very important in stabilizing that soup. Okay? So I'll have to let you read that. I like this diagram because I came up with it. So time over 7 orders of magnitude, charge density, what you're pumping, one particular value of strain, shear strain that lets you roll, all of these things roll up. So I like that particular component. So you start here at 0 time and 0 charge density, and there are 2 phases, mishmash, this one and this one. Both of them, you hit them with a pulse, boop, 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 forms the soup, and then out comes the crystal over here. So we have sort of nice mechanistic understanding. I didn't really convey that to you in this small, brief amount of time, but of mechanistic understanding of how all of this comes about. There are many other crystals you can create, many other supercrystals by pumping it differently. And that's my final slide. These we got on the cover, so just bragging, sorry. So this is the polar supercrystal. This was another one where using terahertz light, we can make them dance. You can look that up. So engineering frustration and pushing on them can give rise to phases that are metastable. Thank you.
Session and Joanne, please come up with your first question.
Sure, I'll come over.
Okay, that's better. Also, other people can hear us. Wonderful talk. Thank you. So my question is that there's this 3D crystal that you create, which metastable. What sets the length scale? What sets the lattice constant, so to say, of this new crystal?
Supercrystal. Yeah, that went fast, but it's about 25 to 30 nanometers on each side.
But there must be some energy scales competing that gives you a length scale. So because it could be anything, right? So is it electrostatics competing with something else that gives you this length scale?
Right. So there is a substrate in there too. The film is grown on a particular substrate. So there is a strain mismatch there, right? And so the substrate strain is such that in the beginning, as you grow it, the two mishmash phases are on either side of the substrate. So the average strain is 0, but individual strains are not 0. They are inhomogeneous strain. But what the system does when you do all this stuff is it finds the supercrystal whose strain is exactly matched to that of the substrate. So it becomes homogeneous 0 strain. It sort of gets lattice matched.
And that competes with the electrostatics, which actually is worse in the 3D supercrystal. Is that correct?
Right. So both are important. Elastic and electrostatic are both important. So the elastic strain goes down, and the electrostatic strain actually goes up because you saw all those vectors are doing all sorts of things. So they are going to build up some charge, and the electrical energy actually goes up. But the elastic energy goes down more than the electrical energy goes up, and so it's still good. It prefers that.
Thank you.
Arindam? Just a moment.
So, is there some form of self-organization involved that you just create the mishmash and then you let it self-organize? Is that something which, I mean, okay, I was trying to understand what's the nature of bonding first. That is, at the end of the day, can I call it an ionic crystal or a covalent crystal? It's a supercrystal. Can you categorize it?
The interactions in the supercrystal are pretty much the same as in the individual components because there's no new interaction popping up. So the physics of the materials themselves are actually quite straightforward. It's elastic energy, it's the Landau energy, which is the polarization energy, and the coupling between the two, electrorestriction, and gradient if there are interfaces. That's it. And all 4 of these are well understood. There's no strong electron correlation. There's no magnetism, no nothing here, right? So that's in a way good because then these things are well understood. And now we are looking at complex systems with very large length scales. So we can study complexity in a prototypical model system. So supercrystal has the same 4 components. It's just that the balance of these energies has changed.
So what's the point in calling it a supercrystal? You're essentially repeating the same structure over the infinite.
Oh, no, it's not the same structure. So the original crystal has this mishmash. One of them has just is quasi one-dimensional. They're little coils and little tubules. The other one is just in-plane domains. It's the standard ferroelectric stuff. The supercrystal has these periodicities in all 3 dimensions. 2 of those didn't even exist before. They're new emergent periodicities. It's not the same at all. Actually, it's a topological change. So in some sense, flooding the interface is like cutting some bands and creating new topologies.
All right.
One quick thing. So why did you have those sunshine phases in the BTO, why did you get the monoclinic phases between the orthorhombic and tetragonal?
Right. So thank you for that question. I eliminated that slide because I was already running over. But it's, again, the local strain and field. So you might have seen that there are one set of domains like this and one like this, and they run into each other. They don't really want to go across. It's like traffic here. So one of them has to come to stop and wait until something happens. So in this particular case, locally, there is a shear strain that's created around those needle points. And that shear strain will shear a 90-degree wall into 90 degree into 89 point something. And because strain and polarization are coupled, there'll be local fields also, about 1 million volt per centimeter. I mean, it's pretty significant. So these two stabilize that monoclinic phase.
Any question from the students or faculty is asking?
Yeah. So you are getting the supercrystal by one pulse. So if you hit with another pulse, what will happen after that?
Oh, yeah, very, very good question. Depends on what the second pulse is. But once the first pulse is created, it's quite stable to further pulses. But I think I flashed through a last slide, but if you pulse it, that one pulse transformation, you have to hit it with certain energy, certain fluence, and then the exposure could be short. But let's say I hit with less energy, but for a longer time and do various series of pulses, then something else shows up. So there are 4 or 5 supercrystals that we now have. Each one can be studied for years. It just gets overwhelming after a while, but it's very rich in that sense. Right. So, yeah, so you can hear me, right? Yeah. So all those shapes are coming from the point group and from Neumann's principle, which says that every property of a system must at least have the symmetry of the underlying symmetry of the crystal structure. So if the crystal is tetragonal, the point, any property, not just optical property, elasticity or whatever, must at least be tetragonal. It could be higher than tetragonal, but it must be tetragonal. So that determines the form of the tensor and so on. On a practical level, how to fit all of that data, we have released a code called SHARP, SHAARP, here 2 A's, second harmonic analysis of anisotropic rotational polarimetry. They are open source codes and they let you do complex things, many layers, shine light, various orientations. It gets very messy and complicated, especially with electromagnetism, but this code lets you do it. It's very powerful. It's open source. You can take a look.
Yeah, I think we have more questions also in the chat, but
right,
because
right. We are running late, and I appreciate it. I'll try to maybe capture those.
Yeah,
I'll send them. Yeah.
Okay, let's then thank Professor Venkatraman with a big applause for a nice talk.